because that's been an issue. Yep, looks good. Okay, so today we're talking about how to solve a problem using the force concept model. This is the force concept model, and since all of you have been in elementary school, I am confident you can tell me what a force is. Can you tell me? Give me the third grade definition of force. Push or pull. That is the truth. A force is a push or a pull. So you don't need to have a bigger understanding of what a force can do. It can push or pull. But what I do have to have you understand is that that's probably not all there is to the story. It's just a start. So when we are tasked with solving a problem, the first thing you have to understand is what is the best part of physics that can be used to solve this problem. That's usually the hardest thing on the AP exam, is to figure out which unit of physics is the one that applies best to the problem at hand. I'm here to tell you that Newton's laws can solve every problem in physics, period. But they are the absolute hardest way. Everything we learn after this is an easier way to solve the problem. So Newton's laws will solve any problem, but they are the hardest method to use. However, they are the only way generally to find an acceleration. They are the only way. Meaning if you want to observe what's happening in nature and predict an acceleration, Newton's laws do that particularly well. Energy is good for velocity, and momentum is good for collisions, but force, it's probably best for acceleration. A Newton's law problem is going to ask you either for the acceleration or for the size of an individual force. A Newton's law problem is going to ask for an acceleration or for the size of an individual force. That is actually all Newton's laws can tell you, is an acceleration or the size of an individual force. They can cloud it with other stuff. They can make you use that to solve something else. But this process that I'm about to teach you can only solve for an individual force or solve for an acceleration. So, in being tasked with solving a problem, and at this point, I'm going to go through this process and then we will apply it to an example. The first thing you have to ascertain from your problem is whether you believe it is a first law problem or a second law problem. Meaning you have to ask yourself if you think net force equals 0 applies or net force equals MA applies. Now, it's usually pretty easy to figure this out. The first law applies in all cases where the velocity is a constant. Students screw that up, though, because they believe that moving means that the forces are unbalanced, and that's not what's being said here. Moving is fine. An object can be moving and still have balanced forces. When you're driving on the highway at 50 miles an hour, the forces are still balanced on your car. Friction, air resistance, the force of the road, the force from the engine, they're all just balanced. The only time forces are unbalanced is when your object is accelerating. If an object is accelerating, it's a second law problem. So when faced with a problem, your first task is to decide if it's a first law problem or a second law problem. Make a mistake here, and you understand the rest of the problem is garbage, right? So you really have to be focused here. On the other hand, if you don't know, then you have to default to the second law. If you don't know, you default to the second law and prove whether there's an acceleration or not. They could ask you if the object is accelerating. Well, we start with the idea that it is until proven it's not. All right? So the first job is to determine whether it's a first law problem or a second law problem. After this, you're going to try and determine which forces you think are acting on your system. And that process we combine with something called drawing a free body diagram. Now, before I go into an example, it's important that you understand what you have to choose from. There's not a limitless number of forces. In fact, in our class, we're probably only going to have like 3 or 4 different forces that are acting in any one problem. And that'll be enough. But it is appropriate at this moment that we talk about what forces are. I know we said push or pull, but we actually have a specific group of forces that we use, and they have specific ways in which they work in our systems. And you can't go outside of these rules. So let's talk for just a minute about the categories of forces. The first ones are what are known as the fundamental forces, sometimes called the conservative forces. They're conservative because they conserve energy. But I would probably more likely refer to them as the fundamental forces. The fundamental forces are different from other forces we've talked about, or other forces you've talked about in other classes. And I want to be really clear about it. I'm separating out the fundamental forces, and normally I would have a day where we would just talk about the fundamental forces and intrinsic properties and stuff, but I have found that students just don't really appreciate it enough, and we lose the day. So I do want to take a moment here to discuss the fundamental forces because of how special they are. How special they are. And I'm going to list them here. There's gravity. There's the electromagnetic. There's the weak nuclear. And the strong nuclear. These are the 4 fundamental forces. They're also called the 4 fundamental interactions. Now, we call these forces, but the truth is these are much bigger than forces, which is why in most textbooks today and in most physics discussions, we say that these are the 4 fundamental interactions. I'm saying that because these 4 things is how all energy is moved around the universe. It's hard to understand that completely, but these interactions is how everything interacts in the universe. Nothing in the universe interacts outside of these 4 things. I mean, we're going to talk about all these other forces, but all these other forces actually only exist because of these 4 interactions. These interactions are weird. They're interesting. They're dynamic, but they're also completely not understood. We don't know what any of these things are. We just make them up. We've given names to things that we've experienced in nature, but we don't know what's going on here. And I know you guys think you have a handle on stuff. Trust me, you really don't. Now, some of these I think are obvious, or at least you might think are obvious. Like if I ask you what gravity is, most of you have an answer to what gravity is. You know, it pulls things towards the earth. No big deal. If you drop your pencil, how does the pencil know which direction the earth is? I mean, how does it know? No, it's definitely not magnets. The thing is, nobody has an answer to this question. You can grab the most decorated physicist and they can't tell you why the pencil goes down. There are theories, and the theories are outlandish. I mean, I'm a field effect theorist by training, and what that means is I believe that the Earth has changed the space around itself and has made a dent in space, and we're kind of falling into that dent. That's what gravity is to me. And I like that definition because I can visualize a guy standing in the middle of a trampoline and little balls rolling in towards him. It satisfies my need to have a visual representation of what that must look like. But the truth is we have no idea why things fall towards the earth. None. Because the one thing all of these share in common is they all act without contact across space. In the same way that I fall towards the earth, so does the moon. And we are pulled around the sun under the same force. It's just trippy. It acts over amazingly large distances. I have no idea how. Nobody does. And in fact, bigger than that, there are other theories. And some of them are just crazy. Like there are people who are particle exchange theorists who believe that the Earth and I are exchanging a set of particles called graviton particles. And it's those particles that carry with them information about force to let my Let me know what direction the Earth is and how hard the Earth is pulling down on me. I don't know that that is any less crazy than the Earth making a dent in space. I really don't. So I just picked the one that works for me. We know a lot about how these things behave. We know nothing about why. Nothing. And every one of these, we have information about it. Like we know that gravity acts on all objects that have gravitational mass. I'm using the word gravitational mass here because I have to. Because each one of these forces acts on a different intrinsic property of matter. Now, you don't know this word, and I don't want to define it because I would do a terrible job. Intrinsic means to be a part of the nature of something. That's the meaning. Look it up in the dictionary, that's what you're going to get. That really doesn't help you out, though, too much, does it? It's like saying, what does it mean to be human? I have no idea. Pick a feature, and you could probably tell me somebody that doesn't have that feature. But generally, if I show you a picture, you can probably pick out the humans. Why? There are features of humans that we all tend to have in common. And we tend to think people who don't have those things are weird or something's wrong with them. So we tend to think 2 arms, probably. Head, yeah, likely. Torso, I hope so. But, that really described a lot of stuff there, didn't it? Somehow we can kind of identify the humans from the things that are not human. Why? Because there's some property about them. Intrinsic means to be a part of the nature of it. This, at a holistic level, down to the very fiber of the universe, there are intrinsic properties, something about matter that creates gravity. And we believe mass creates gravity, and gravity acts on mass. It's not one acts on the other. They are linked together. The creation of mass creates gravity. That's why this is weirder than I want to let on. It's not just stuff being pulled downwards. Each one of these is like that. The electromagnetic force, similar. It acts on the intrinsic property you learned about in chemistry called charge. You didn't learn very much. You probably learned +1, -1, stuff like that. Electrons are negative and protons are positive. That's probably the extent of your knowledge of charge. But there's a lot more going on here. For example, the electromagnetic force is the only one that can push. It's the only force in all of these, in all of nature, that repels. Every other force in nature is an attractive force, except for the electromagnetic force. It'll repel. No one knows why. But you guys already knew this. Of course, Miss Shelton, opposites attract, likes repel. Yeah, it's that easy. No, it's not. You know what's weird is only things with charge experience this force. There are lots of things without charge, they don't experience this force. They are invisible. The neutron is invisible to this force. Weird. Like it just doesn't get seen. If you wanted to pick something up, you would grab it, right? If I wanted to move an electron, it's a little harder, it's small to grab, but I can push it around because it has charge. I can find other things that are negative or positively charged and push that electron around like I would a paperclip with a magnet. But you guys know that there are things that magnets don't stick to. Same idea, the neutron. How do you pick up a neutron if you can't push it around with that force? You have to find another force you can push it around with. It's actually kind of hard to do. So again, the electromagnetic force is the intrinsic property. There's charge. I don't know anything about this one. When I say we don't really know what's going on in the universe, I don't mean that haphazardly. When I went to school, when I was in your seats, this was a force. When I went to college, this was no longer a force. We only had 3 fundamental interactions. When I exited college and started teaching, somewhere between my first couple of years of teaching and now, it became a force again. In one of those editions of the books, I'm sure I could pull it out. It'll show me that there is no weak nuclear force. And then in the very next edition, there is again. We have no idea what it is. I can't even tell you what it acts on. I can tell you that they believe the weak nuclear interaction controls radioactive decay and radioactive changes. It is the interaction that can cause a proton to become a neutron. I don't know if you know that happens, but it does. And neutrons can become protons. It happens spontaneously. We have no idea what the mechanism is. We can't speed it up or slow it down. It just happens. And then there's the strong nuclear. Strong nuclear force is an attractive force between nucleons. It's an attractive force between nucleons, protons and neutrons. That's it. The electron, it's invisible to the electron. The electron isn't pulled by this force at all. But protons and neutrons, there. But it's not obvious how that works. 2 protons? Nope. It won't work. Proton, neutron? Yep. Proton, proton, neutron? Yep. Proton, neutron, neutron? Nope. It's like some weird, like, particle orgy that has to happen just right for it to work out the way it is. And if it doesn't work out just right, nope, we don't go together. Nope, sorry. It's that weird. But you can have a proton, proton, neutron, neutron, that works. You can have a proton, 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 neutron, neutron. But eventually, one of the protons will jump the fence and become a neutron, and then it'll just be a proton, proton, neutron, neutron, neutron. Figure that out. We have no idea. No idea. I mean, it's a mad scientist out there. But I will say, and this is what I want you to know, that this is the order of weakest to strongest. Although we think the gravitational force is overwhelming, it is the weakest of the fundamental forces. Which is also why, when you go from the top to the bottom, the amount of energy you get from these interactions increases. You see, force is the method by which energy is transferred. We'll learn that later, but it's important now. These interactions is how all energy gets transferred. A nuclear power plant clearly works because of this interaction. But if you want to burn fossil fuel, well, then you're going to be burning something here. You're going to be using the electromagnetic force. That's where that energy comes from. A dam, that's gravitational force, just pulling the water down. Even hydroelectric power is just gravitational force. It takes a lot of water to do the same thing that a bunch of gallons of natural gas will do. And it takes a lot of natural gas to do what just a couple of atoms of hydrogen will do for the weak nuclear, or for the strong nuclear force. So it's amazing. The amount of water that would fit in Tampa couldn't fall over a dam and power our city. But the amount of nuclear fuel that could fit in my big cup could power this city for a year and a half. Kind of unbelievable how much energy there is when you start going down this scale. And each one of those represents how much bigger the force is as you go down the scale. Now, I say all this to you because I want you to have this idea of what's happening. But ultimately, the only one of these that's going to matter for us is weight, the gravitational force as we experience it on our Earth. Because for the time being, that's about all we can handle. It's nice to talk about these, and I want you to know the names of the 4 fundamental interactions, and I would like you to know the order from weakest to strongest. I want you to know those things. I want you to know that they all act without contact across space. I want you to know that, and that we don't know how or why. And I'd also like you to know that each one acts on its own unique intrinsic property. I want you to know those 3 things. They all act in this order of weakest to strongest. They all act across space without contact. And they all act on a unique intrinsic property of matter. But for our class, unfortunately, for the time being, we are going to focus on only one of them. And that's going to be the weight. Weight is the force of gravity on objects near the surface of a planet. That's weight. Weight is the force of gravity on objects near the surface of a planet. The objects have to have mass to experience weight. And it's appropriate that you understand that weight is mg, meaning when we calculate, when you drop something, the unbalanced force acting on it is gravity, so it will accelerate. All things accelerate at g. So the weight of an object is equal to mg, the result of ma acting on an object. That means the m part here is the mass of the object. And this must be the gravitational mass of the object. But what's interesting, and not something I will test you on, is that gravitational mass and inertial mass happen to be the same thing. The m we talked about yesterday in ma is inertial mass. The m we talk about here is gravitational mass, and it has now been shown that those are the same measurement. So when we talk about mass, we are talking about both the inertial mass of the object and the gravitational mass of the object. Yesterday I said inertia is how much an object resists changes in motion. And now we also know that the gravitational mass is how much gravity an object experiences. They're the same. Now, whenever we have the weight of an object in a problem, we will be replacing weight with mg. And m has to represent the mass of the object we are looking at. So the fundamental force of gravity is the one that we're going to use as our group of forces that act on objects. Our objects are always going to be experiencing the force of weight. So it's going to be pretty easy to make sure we label that one. And I'm going to use a capital W for weight. I tend to be a single letter person when it comes to the forces. Your book, however, wants you to do F with a little w next to it, or F with a little g next to it. I'm not going to do that, because if there's 5 items, then you're going to have FW1, FW2, FW3. That's a lot of F subscripts, and just W. So W is the force of weight in our problems. I will use a capital W to represent weight. The next forces are the contact forces. They are easier to talk about, but they have very specific requirements. Meaning, once you learn about a contact force, or once you know a contact force is acting in your system, it's going to act in a very specific and particular way. So we're going to go through a list of the next 4 forces. Each one of them has a specific context in which it is used. The first contact force are pushing forces, and we call these normal forces. They are not normal because they are ordinary. They are normal because they are perpendicular to the surfaces in contact. Perpendicular to the surfaces in contact. It's appropriate that you understand that when I say that, I mean it. The normal force is perpendicular to the surface. Right now, your pencil lead is experiencing an upward force from the paper. Because the paper is horizontal, the normal force on the pencil lead has to be upwards, because that is perpendicular to the paper. If you're leaning back in your chair, like some of you are, then you are experiencing a forward force. The normal force from the back of the chair on your back has to be forwards, perpendicular to the back of the chair, in the same way that the floor is applying an upward force to the soles of your feet. Has to be upwards because it's perpendicular to the floor. The normal force must be perpendicular to the surface that is in contact. You don't get to choose the direction of this force. It is chosen for you. I will use a capital N for normal forces. Pulling forces are tensions. I'll use a capital T. Now, I want to be really careful here, because I'm going to say they can act in any direction, but that's not true. Because you can't push a rope. So I don't think I have to say it like that, but if you have a rope, you can't push it. You can only pull on the rope. However, the rope can be pulled at almost any angle away from an object. When it comes to tension forces, there is a conduit, something that connects you with the object you are pulling on. A string, a rope, a cable, your arm. So if you grab something and pull on it, the direction of that string or cable or arm is the direction that that force acts. So tension forces can act in almost any direction away from the object. Again, when I say any direction, it's true, but it's any direction away from the object. So those are it. Those are the contact forces. We have resistive forces. Resistive forces. And I think they're obvious in what their nature is. They try to prevent an object from moving. That makes it pretty clear that they're going to act in a direction that prevents motion. There's only 2 of them that we're actually even going to talk about, and only one of them that will probably be mathematical in nature. The first one is friction. I will always use a lowercase f for friction. Friction attempts to prevent one surface from sliding across another. Friction is a force that attempts to prevent one surface from sliding across another. Now, a couple things about friction, or a simple thing about friction. There is no friction if there's no normal force, right? There has to be a surface in contact for there to be friction. If there's no surfaces in contact, there can be no friction. So if there's a normal force, there's potentially a frictional force. And if there is a frictional force, there's definitely a normal force. More than one normal force can result in more than one frictional force. Right now, your feet and arms are both in contact with different surfaces. Probably both of them are providing frictional forces. The last one, we won't probably do very much with it. I say air drag, but it really should just be drag, because this is the force that you experience when moving through a fluid. It's a resistive force. I'm going to put F with a little D next to it, but I never use it. It's a resistive force, meaning when you try to move through a fluid, this is the force that tries to prevent you from moving through a fluid. Air is a fluid, so if you try to walk through air, you experience air resistance. Water is a fluid. If you try to walk through water, you probably experience a greater amount of drag. Drag is complicated because drag is proportional to velocity. So the faster you go, the more drag you experience. That makes it mathematically complicated. There are other forces in nature. We're not talking about them right now, but there are others. There's the Bernoulli force, which deals with air pressures. There's the buoyant force, which is what buoys you up to the surface when you're in a fluid. There are other forces. These are the forces we will talk about in this class. Now, I've gone through all the forces because when you're tasked with solving a problem, you have to ask yourself which of these forces are likely acting on the system in which you're observing. Each one of them now you know acts in a particular direction and in a particular way. So when I tell you that it acts normal to the surface, you have to draw a picture in which the normal force is acting perpendicular to any surfaces that happen to be in contact. What we're going to do real quick is we're going to do an example. So although I've highlighted all of the forces that act in a system, I want to talk about how these 4 steps are used to solve a problem. And it's going to be a ridiculously silly problem, and that's purposeful because it's not about the actual problem, it's about how we apply Newton's laws to solve a problem. So I want you to imagine, you don't really have to imagine much, a book sitting on a desk. So there's the book sitting on a desk. We're going to attempt to apply Newton's laws to this problem. Now, I didn't ask a question. Applying Newton's laws isn't a question, it's a process. At the end of the process, you could probably answer relevant questions. So the process begins by you asking yourself whether the book is experiencing a Newton's first law situation or a Newton's second law situation. Is the book accelerating or not? Can we all agree that the book is not accelerating? So that makes this a Newton's first law problem. The next step is for you to draw a free body diagram to represent the forces that act on the book. And that's our next step, is to draw a free body diagram that represents the forces that act on the book. So a free body diagram begins with a dot. A free body diagram begins with a dot. Each object you're observing is represented by a dot. The dot represents the center of the object. Newton's laws apply to one object at a time. Next, I'm going to go through my list of forces. I'm going to draw an arrow to represent the size and direction of each force that acts on the object. The size and the direction. Each arrow will start at the dot and be drawn outward Unlike what we did for adding vectors together, a free body diagram, all the arrows originate at the center of the object. We're going to start at the top of the list and ask which of the forces are likely acting on the object based on the situation we're observing. For example, do we believe gravity is acting on the object? I think that seems reasonable. I'm going to draw an arrow that is straight down. The size of this arrow is important because it will set the scale for the rest of your drawing. So I'm not saying that there's a particular size that you should draw here, but if you know if one object is greater than another, you should draw its arrow bigger than the other object's arrow, things like that. There, we've exhausted the fundamental force, so now we're going to go through all the contact forces. Is the object in contact with the surface? Sure is. So I need to draw another arrow. I don't get a choice on how this arrow is drawn. It must be drawn perpendicular to the surface in contact. Not that that's hard. I'm pretty sure that means up. So I'm going to draw another arrow straight up. Now, I forgot to do this. I need to label the arrows with the type of force that I believe they are. So normal force gets a capital N, weight gets a capital W. And I'm going to make a reasonable attempt to try and look to see whether I am striking the situation at hand, which is supposed to be balanced. I don't think my normal force was drawn long enough to really suggest balance. It looks a little short. So you should be attempting to make a reasonable attempt to try and demonstrate the balance here. So I'd probably make it a little taller to try and strike balance. But I'm not done with my list. Are there any cables, ropes, strings attached to the book? So I don't see any reason to put a tension force there. Is the book attempting to slide across the table? No, it's unlikely that it's experiencing friction. And if it's not moving, it can't experience drag. Drag can only be experienced while moving through a fluid. It has to have a velocity. So no air resistance. We have exhausted the forces acting on the object. So our free body diagram is nearly done, but there's something else that I will expect you guys to do, and that is apply an appropriate coordinate system. Now, this part sounds stupid easy. It is not. This is probably the hardest part that students have. You have to apply X and Y to your system because Newton's laws are one-dimensional, meaning we can only do math in one dimension. So we'll be breaking our problems up into an X dimension and a Y dimension. You can choose a coordinate system that is lined up any way you want. As long as the X and Y are perpendicular to each other, you can line up your coordinate system however you wish. But remember, if you have any force that is off axis, it will have to be resolved. You will have to do trig and find out how much of that force is on each axis. So this would be a stupid coordinate system for this problem. It would probably make a lot more sense for me to line up my coordinate system with the forces that are there. When employing a coordinate system, I will give you two pieces of advice. One, always line up the coordinate system with the direction of motion. You'll be happier. Always line up the coordinate system with the direction of motion. Failing that, then attempt to line up your coordinate system with as many forces as possible. I know it's a weird thing to say, but I'll say it again. Either line it up with the direction of motion or try to line it up with as many forces as possible. So I am going to line mine up with as many forces as possible, which means I'm going to put the Y direction right there and the X direction perpendicular to the Y. So I have applied a coordinate system to my free body diagram. The last step is to apply Newton's laws, but this part seems ridiculous, but it's really not. Newton's laws, although suggest we can apply them in all directions, our mathematics do not. So we have to take this and break it up into two. Net force in the X direction and net force in the Y direction. Because this is a first law problem, they are both set to 0. If it was a second law problem, we'd have to hopefully just set one of them to MA, unless it's accelerating in 2 dimensions, which would be no fun at all. Now, here's where I know I got 3 minutes. I'm using all of them. Newton's laws aren't equations. When I say apply Newton's laws, what I'm actually stating is follow the set of instructions that are given. Newton's laws are a set of instructions. They are not equations. Newton's laws state, add up all the forces in a particular direction and set them equal to 0 or ma. It's a set of directions. You are creating a custom equation that will solve this problem, and you're following instructions on how to do so. Again, this says, add up all the forces in the x direction. That's what that says. Now, there are no forces in the x direction here, but there are forces in the y direction. So I will do the next one. Add up all the forces in the y direction. I have 2. There's positive normal force and negative weight. It's at this moment that you apply direction based on the coordinate system you drew. And set that equal to 0. When you are using Newton's laws, you are generating a relationship between the forces. You are creating this relationship that will be used to solve this problem. Now, I don't know what the problem was. I didn't give you a problem. But I can tell you after executing my series of rules, I can tell you that the normal force equals the weight. The book is pushing on the table is pushing on the book. I can tell you more than that. It's a 2-kilogram book. Since weight is equal to mg, I could write this as normal equals mg. And like I said, the mass of the book is 2 kilograms. That's 2 kilograms times 10 meters per second squared. G is 10 meters per second squared still. Now, this means that the normal force on the book is 20 kilograms meters per second squared. That is the unit of force. That is a complex unit, and it's given the name Newton. It is 20 newtons. The unit of force is the Newton, and it is a kilogram meter per second squared, a complex unit. All right.